Hello everyone. So this is the fifth part of chapter 9. So in this part we will see some design aspects of shell and tube heat exchanger, some design and configuration parameters. If you change them, then how it is going to affect your heat transfer coefficient and pressure drop. Okay, so as we can see on our screen, um, that we have heat transfer and Nusselt number correlation. So the Nusselt number is directly proportional to the Reynolds number and the Prandtl number. And from the Reynolds number, we know that Reynolds number is directly proportional to the velocity. So we can say that the Nusselt number is directly proportional to the velocity to the power 4 over 5 or velocity to the power zero point 0.8. So if we change the velocity, then the Reynolds number will be changed and the Nusselt number will be changed. Okay, so how can we change the velocity? If we change the shell and tube heat exchanger configuration, for example, if it is one pass, then all the tubes takes the fluid from one end to another end and then delivers. So if your heat exchanger is two pass, then half of the fluid takes the tube, half of the tubes takes the fluid from one end to other end, and then another half of the tubes that takes the fluid from one end to another end. So basically, when it is one pass, then all the tubes takes the fluid, and when it is two pass, then half of the tube takes the fluid. So if the flow rate is same in both the case, whether it is one pass or two pass, then if it is one pass, then the velocity in the tubes are less because all the tubes are taking the fluid from one end to another end. When it is two pass, then when half of the tubes are taking the fluid, so that means the area is reduced and the number of tubes are reduced, area is reduced, so the velocity in the tube becomes double. So as you increase the number of passes, the velocity is multiplied by the number of passes. And when the velocity is multiplied, then the Reynolds number is multiplied. When the Reynolds number is multiplied, then the heat transfer coefficient is directly proportional to the Reynolds number to the power 4 over 5, or heat transfer is proportional to the velocity to the power 4 over 5 means 0.8. Okay. So ultimately we can say that the heat transfer coefficient is directly proportional to the velocity to the power 0.8. Similarly, if we talk about the pressure drop, so the pressure drop expression delta PT is equal to 1 by 2 rho V square. So here the pressure drop is proportional to the square of the velocity. So if you change from one pass to two pass, then your pressure drop will be changed drastically because it's a square. And furthermore, if it is one pass, then the flow path is equal to the length of the heat exchanger is traveling from one end to other end. But when it is two pass, then the flow path gets double because the fluid is going from one end to other end and then coming back. So basically, it travels twice the length of the heat exchanger. So as the number of passes increases, the length of the flow path increases and it is multiplied by the number of passes. So when it comes to the pressure drop, then we are having two factors. One is the length. If you are increasing the number of passes, then the velocity is increasing and the length is also increasing. So for the pressure, there are two contributing factors. One is the square of the velocity and the length. So when you change any heat exchanger from one pass to two pass and two pass to eight pass, so when it is two pass, then its velocity is multiplied by 2, and when it is 8 pass, then the velocity is multiplied by 8. So if we want to find out that what is the increase and what is the ratio when it is 8 pass and when it is 2 pass. So when the heat exchanger is 8 pass and when the heat exchanger is 2 pass, and when you take the ratio of the heat transfer coefficient, then heat transfer coefficient, which is directly proportional to the Reynolds number, and Reynolds number is directly proportional to the velocity to the power 0.8. So from this expression we can write that if it is 8 bars, the velocity gets 8 times, so 8 vt raised to the power 0.8, and when the velocity is when the number of passes are 2, the velocity gets twice, so 2 vt raised to the power 0.8. So this factor gives you that how much will be the increase in the heat transfer coefficient when you change from 2 pass to 8 pass. So it increased by 3 times, 3.03. So it is increased by 3 times. So this is about that you are making any modification in the configuration that from 2 pass to 8 pass. So it can be done for any number of passes, and we can find that how much is the heat transfer coefficient effect. So when we look at the pressure drop, so what happens, the pressure drop is proportional to the v square as well as proportional to the length of the flow path. So when it is 2 pass, then the length is multiplied by 2, and when it is 8 pass, then the length is multiplied by 8. Similarly, when it is 2 pass, the velocity is multiplied by 2, and when it is 8 pass, velocity is multiplied by 8. So when we calculating the ratio of the pressure drop when you change the heat exchanger passes from 2 to 8, then we can write this expression in this form and find out that what is the increase in the pressure. So the pressure drop is increased by 64 times when you change the passes from 2 to 8 passes. So what we can see from here that the pressure drop increased drastically, and the pressure drop becomes 64 times when you change the passes from 2 to 8. However, the heat transfer coefficient is increased only by 3 times when you change the number of passes from 2 passes to 8 passes. So this is the effect when you change the configuration for the tube side. Now we will see that if we change the configuration at the shell side, then what is the effect on the heat transfer and pressure drops. Okay, so the one of the parameter of the shell and tube heat exchanger shell side is the Waffle spacing. So if you increase or decrease the Waffle spacing, then the area of the flow will be changed, and the pressure drop will be changed, and the heat transfer coefficient will be changed. Okay, so the maximum Waffle spacing, it can be equal to the inner diameter of the shell. If your shell diameter is 400 millimeter, then the maximum Waffle spacing should be equal to the inner diameter, which is 400 millimeter something. Okay, what is the minimum Waffle spacing? The minimum Waffle spacing is the inner diameter of the shell divided by 5. So this is the minimum Waffle spacing. So we can get now what is the maximum Waffle spacing and what is the minimum Waffle spacing. Okay, so now we will consider these modification for the shell side. So what we can modify for the shell side. So the one of the modification is that we have the baffles, number of baffles. So you can change the number of baffles. You may increase and you may decrease. So this is one of the aspect of shell side parameter variation. What other parameter we can change, except that we can change the number of baffles. Now come for the shell side. So when we talk about the shell side, then our heat transfer coefficient is proportional to V raised to the power 0.55, and the pressure drop is directly proportional to the velocity square and multiplied by NB plus 1. So this NB plus 1 basically representing the length of the flow path, and Vs is the velocity in the shell. Okay, so when we talk about the Waffle spacing for the shell side consideration, that The maximum baffle spacing can be equal to the inner diameter of the shell, and the minimum baffle spacing can be the inner diameter of the shell divided by 5. So if you take the two extremes, that you have baffle spacing equal to the inner diameter, and in other case you have the baffle spacing which is equal to the inner diameter and divided by 5. So you reduce the basically this baffle spacing by 5 times. So the number of baffles supposed to be increased by the same by the 5 times approximately. Okay, so when we are changing the baffle spacing, so when we have the baffle spacing equal to the ds, then we have velocity vs. So when you reduce the baffle spacing by 5 times, then the velocity becomes 5 times higher. So this is how we represent that what will be the effect on the heat transfer coefficient if we are changing the baffle spacing and we are reducing the baffle spacing by 5 times. Okay, so this is about the heat transfer coefficient ratio. Now what about the pressure drop? The pressure drop, when it is when the baffle spacing was equal to the inner diameter, then the velocity was vs, and when the baffle spacing is reduced by 5 times, the velocity is increased by 5 times. So this is the velocity contribution, and then the other term 5 over 1, this is the length contribution. So when it is one pass, the length is equal to the one length is multiplied by one factor, and when the baffle spacing was equal to the inner diameter, when the baffle spacing is reduced by 5, then the length of the flow path is basically increased by 5 times. So this is the factor of the due to the increase in number of baffles, baffles. Okay, so when you take this ratio comes out to be 125. So what we can see from here, that if we talk about the shell side, and when you are reducing the baffle spacing and you are increasing the number of baffles, then the ratio of the heat transfer is just 2.25. So that means there is some increase when you reduce the baffle spacing, and it is 2.24 times increased the heat transfer coefficient. Oh, I'm sorry, it's increased, right? Okay, so what happens on the pressure? The pressure is increased by 125 times. So it's a big jump in the pressure when you change the baffle spacing. The heat transfer coefficient is only increased by 2.24 times, whereas the pressure drop is increased by 125 times. So this is about the different configurations, and when you change the configurations, so how is it going to affect your uh, how is it going to affect the heat transfer coefficient and pressure drop? So then we can basically look at that, what are the important points. So the sizing method is carried out by assuming heat and trial. For that the heat exchanger, right, the trial size should be the trial size the trial size should be rather small, with the objective being to select the smallest heat exchanger that will work subject to the following constraint. So the exchanger should be small as possible. The correction factor F should be equal to or greater than 0.75. So basically the minimum correction factor should be 0.75, and the victory of the tube fluid should be the velocity of the tube side should be in the optimum range, whereas for the shell side it is not mandatory to keep the optimal velocity, because the shell side usually there are baffles and the flow is zigzag. Okay, so These are the things that we need to consider when we are dealing with the shell and tube heat exchanger configurations. Okay, so and other things we know that when it is new and when it is old. So when it is old, uh, and then the following factors must be taken into account. And then there is a pressure criteria for 70 kilopascal for any fluid, that the maximum pressure drop should not exceed 70 kilopascal.